VSEPR theory, valence shell electron repulsion theory. Electron pair repulsion theory, I should say. A Lewis structure is a two-dimensional representation of a molecular model or a molecule representing non-bonding and bonding electrons of different elements in a compound, usually to satisfy the octet and the lowest formal charge of resonance structures. Now, are these structures good indicators of what molecules look like three-dimensionally? Good example is, let's do the Lewis structure of water. We have oxygen bonded to two hydrogens, right? Now, a lot of the time students will draw this, right? You have your oxygens and your two hydrogens, each follows the octet, and you have your total electrons. Now, when you actually make the model of water, you get this structure. Do you see how this is not linear? Here's your oxygen, you have your two hydrogens, and they're bent, so it's not a linear structure. So there's a difference between the three-dimensional model and the two-dimensional representation. So valence shell electron pair repulsion theory, in short-term VSEPR theory, is based on the simple idea that electron groups repel each other through Coulombic forces. In chapter 8, we talked about how there's attractions and repulsions going on. So we have to think, okay, well, in this bond here, right here in this bond and in this bond, we have two electrons. So these two electrons are repelling one another because they don't want to be together. They also are being attracted towards the nucleus of the oxygen and the nucleus of each hydrogen. So there's attractions and repulsions going on. Because of these repulsions and attractions, the molecule bends the bonds in different ways because the electrons don't want to be together, causing a different three-dimensional shape. The electron groups are attracted to the nucleus, but the VSEPR theory focuses only on the repulsion. So don't forget that there are attractions going on, right? So if I show you, if I have my hydrogen, right? This is my hydrogen atom, and I have my proton on the inside. And then I have my bond with my electron and my other electron, and then I have my carbon atom with the nucleus inside. So these electrons are repelling each other, but this electron is also attracted to this proton, and this electron is attracted to this proton. So there's repulsion and attraction going on. For VSEPR theory, we're focusing on the repulsion and how that causes the shape to be different three-dimensionally than what we see in a planar piece of paper. The repulsions between electron groups on interior atoms of a molecule determines the shape, the geometric shape. So we first look at, just through the electron groups that we have, what would be the shape three-dimensionally for a structure. The preferred geometry of a molecule is the one in which the electron groups have the maximum separation. Now, why is this important? Why do we want maximum separation? Electrons don't want to be together, so the most stable structure is to get those electrons as far apart from one another as possible. So, little diagram here. You see that the electron groups are repelling each other. If we have this as my central atom and I have three bonds around it, the electrons in the bonds are repelling each other and the electrons from the other bonds, whereas attracting towards the central atom, causing a different shape. For the first part of VSEPR theory, we're going to look at the 5 main electron groups. So we're only looking at the total amount of electron groups we have around the central atom and how that's going to affect the shape. The Lewis structure predicts the arrangement of valence electrons around the central atom, or atoms, if we have more than one. Each lone pair of electron constitutes one electron group in a central atom, and each bond constitutes one electron group in a central atom. So if we look at this structure here, right? Now, I know that I can figure out how many bonds and lone pairs I have around every atom, but I only care about my central. Now, my central atom has 1, 2, 3 electron groups. Even though there's 2 bonds, I'm not counting the bonds individually because I'm looking at on each side of the atom, remembering that my atom is a square, how many groups of electrons do I have on one side? So this double bond is 1 group. This lone pair is another, and this bond is another. 3 electron groups total. Now I want to get a little bit more specific. Out of those groups, how many lone pair groups do I have? I only have 1 lone pair group. Out of those 3 groups, how many bonding groups do I have? Now this is another important thing. It doesn't mean how many bonds I have, it means how many bonding groups. I have 1 group of bonds on this side and 1 group of bonds here. So I have 2 bonding groups. Now, if asked how many single and double bonds, then you would say 1 single bond, 1 double bond. Your lone pair and your bonding group should always add up to your electron groups. The electron groups is the total what's around your central, and then you specify it with how many lone pairs and how many bonds you may have. So looking at the shape of the molecules from the 5 basic arrangements of electron groups. Based on a maximum of 6 bonding electron groups, which is really rare but exist, each have 5 different basic molecular shapes. In order for the molecular shape and bond angles to be perfect, all the electron groups must be bonds and all the bonds must be equivalent. So basically everything has to work out to satisfy the octet and the appropriate angles. For molecules that have a resonance, it doesn't matter which resonance form you use, the electron geometry will be the same. So for structures where you have 3 different resonance structures where the double bond is moving around, they're going to have the same electron geometry no matter what. So let's practice the 5 basic. First one is linear geometry. When you have 2 electron groups around the central atom, they occupy positions opposite of each other, and you have a linear geometry where the bond angle between the outer atoms is 180 degrees. Now here's 2 examples with a single bond and a double bond where you have a linear geometry. Beryllium, 1 group, 2 group, 2 electron groups, linear. Carbon, 1 group of electrons, 2 group of electrons. Even though they're double bonds, I'm thinking of group, so 2, so still linear geometry. Now, trigonal planar geometry. When I have 3 electron groups around the central atom, occupy positions in the shape of a triangle form. Now, again, double, triple bond, single bonds, it doesn't matter as long as it's a group. 1 group, 2, 3, so trigonal planar. Even though this is a double bond, I still have 1 group, 2, and 3. My bond angle is 120 degrees. Only important thing to note here is because this has a double bond here between the carbon and the oxygen, the bonds are not completely identical. The observed angles are then slightly different because there's a little bit more repulsion in the double bonds. Note how it's still very close to 120, the trigonal planar shape, but just slightly different. Tetrahedral geometry. 4 electron groups around the central atom. They look in the shape of a tetrahedron. So when you have 1, 2, 3, 4 groups around the central, you will have a tetrahedral geometry with a bond angle of 109.5 degrees. Trigonal bipyramidal geometry. 5 electron groups. 5 electron groups give you a trigonal bipyramidal geometry, which actually gives you 2 angles. So 1, 2, 3, 4, 5, I figured out my shape. Then I want to figure out my angles. You have a trigonal bipyramidal, which means that you have your triangle that's kind of on the plane and the line going through it. When the angles that are straight through the line up and down, those are 90 degrees with the creating the atom on the axes. So this chlorine and this create a 90-degree angle. Now from the chlorine all the way to the other plane of the chlorine, it's a 120-degree angle. These are equatorial on the axes, and these on the y-axis, these out of the plane are equatorial, these on the axes are axial. Last one is octahedral. That's when you have 6. So 6 electron groups around the central atom gives you an octahedral shape and always a 90-degree angle. So you can see here 6 groups, 90-degree angle, octahedral geometry. Let's practice. Determine the electron geometry of nitrate and carbon tetrachloride. Nitrate is NO3 minus. Carbon tetrachloride is CCl4. So to determine the geometry, I first want to draw my Lewis structure. Nitrate, oxygen, oxygen, and oxygen. Total electrons, I have 5 plus 18 plus 1, which is 24. So I know that nitrogen has to make an octet because it's not in period 3 or below. So I'm going to give one of the oxygens a double bond, the other two a single. 2, 4, 6, 8. My nitrogen is completely satisfied. Then I just complete the octet for my other oxygens, and then I'll check to make sure that I have used only 24 electrons. Give my minus charge. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Perfect. Now, does this have resonance? Yep, because what's to say that the extra electron was added here and not here or here? So then I would have 3 resonance structures. Now I'm drawing this just for practice, but in answering this question, you actually don't need to draw out the resonance because it's asking only for the shape. But I'm drawing this so you see that the shape doesn't matter for different resonance structures. They will all be the same. Perfect. So now how many electron groups do I have? 1, 2, 3. 1, 2, 3. 1, 2, 3. 3 electron groups. From my notes before, I know that 3 electron groups is trigonal, planar, with a 120 degrees bond angle. Now let's look at carbon tetrachloride. Carbon has 4, chlorine has 7, but there's 4 of them, so 28 plus 4, that's 32 electrons. So carbon will go in the middle, chlorine, 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 and chlorine. Bond that all together. My carbon is satisfied. I write my extra electrons around my outer atoms. Let's count. 2, 4, 6, 8. I have 4 of them, 32. Perfect. There's no resonance here, no charge. Don't have to write it in brackets. I'm done. Now what's my shape? 1 electron group, 2, 3, 4. 4 electron groups. I have a tetrahedral electron geometry with a bond angle of 109.5 degrees.